but we are very thankful to Mr. Enis Soda for his valuable time and guidance for this tutorial. Ladies and gentlemen, today's tutorial is planned for 90 minutes where Q&A session shall be taken at the end of the tutorial. We'll request all the participants to keep posting their queries in the chat box and all the queries shall be taken after the presentation. Kindly avoid any discussions during the presentation to avoid any disturbance to the presenters, please. We are honored to have with us eminent speakers on this subject, Dr. Giovanna Dondasola, Dr. Roberta Derugia, and Dr. Mauro G. Todaschini. From SIGRE India, we have with us Shri A.K. Bhatnagar, Director SIGRE India and Central Board of Irrigation and Power. Without taking much of your time, I would like to invite Shri A.K. Bhatnagar, Director SIGRE India and CBIP for his welcome address. Bhatnagar, sir,
Thank you, Shashank. Thank you, Shashank. Thank you. Good afternoon, ladies and gentlemen. We welcome you all on this online tutorial, international tutorial on cyber security measures for energy system, being jointly organized by SIGRE India under the aegis of SIGRE National Study Committee, NSC D2 on information system and technical communication along with CBI. Series of international tutorials being organized by SIGRE India with the guidance and support of SIGRE study committees and national study committees. And today is the third tutorial in the series under the aegis of SIGRE SC-D2. I am glad to share the excellent support and help extended to by SIGRE India in achieving the objective of dissemination of knowledge effectively during current pandemic situation. It is by Dr. Olga, he is going to join us shortly, and who is study committee D2. And we have also valuable guidance from Debashish Day, who will be joining. He is a current chairman of NSC D2. And Mr. N.S. Soda is a very experienced, eminent speaker, and who is former chairman in NSC D2 and currently advisor, strategic advisory group, SAG of SIGRE SC D2, Paris for the tutorial. Thank you, sir. We are also thankful to Dr. Giovanna, Dr. Roberta, and Dr. Maura, who have agreed to deliver today's tutorial. Thank you so much for supporting SIGRE, and with your support, there will be enhancement in the knowledge of all the participants. It's a very good takeaway for everybody. I have been told that this is the third tutorial by SIGRE SC D2, and the fourth tutorial will be on 19th March 2021 on core IT technologies, AI, IoT, big data, which are powerful tools for energy supply system of the future. I welcome Shri N.S. Sodaji, a very eminent speaker and former chairman of NSC D2 and currently advisor, strategic advisor group of SIGRE SC D2, Dr. Giovanna, Dr. Roberta, and Dr. Maura from Italy, who are delivering tutorials today. I request all the participants to make maximum advantage of their experience and the opportunity in this pandemic also, that we are online learning and enhancing our knowledge. With this, once again, I welcome you all and request all the participants to join SIGRE as its member and connect with global power system community. Thank you very much. Thank you all, and we'll go ahead. Over to you.
Thank you, sir, for your welcome address. Now, moving further, may I now request respected Shri N.S. Soda, Advisor Strategic Advisory Group of SIGRE Study Committee D2 Paris, former Chairman SIGRE National Study Committee D2 and former Executive Director Load Dispatch and Communication, Power Grid, to kindly enlighten the participants with his vast experience on the subject of tutorial. Soda sir, over to you.
Yeah, thank you very much. Am I audible?
Yes, sir, you are audible.
Good afternoon, everyone from India, and good morning to Dr. Giovanna Dondasola and Dr. Roberta and Dr. Mauro, because it's early morning for you. So I welcome you all for this seminar and tutorial online for the Indian audience. I am very much thankful to Dr. Giovanna because she has been our continuous friend for many, many years. And I have heard her number of times in the SIGRE events, and she is really the expert on cybersecurity for power systems and infrastructures. So we are very lucky, all the Indian experts or all the Indian audience that we have today, to have Dr. Giovanna Dondosola and her friends who are themselves known world over. And Dr. Giovanna has been actually instrumental in organizing many documents, particularly on the cybersecurity. And she is a learned as well as well-known, speaker and well-known faculty for the cybersecurity all over the world. So welcome, Dr. Giovanna Dondosola. Let me just clarify that Indian power system is very huge now, with around 374 gigawatts of power being generated, installed capacity, and about 190 gigawatts of power maximum demand. And naturally, the transmission sector and the generation sector are better organized from the IoT angle and from the IT/OT perspective. But when it comes to the distribution segment, we do have very good performing companies like TPDDL and other CESC and other companies. But still on some of the states, the distribution network and the distribution system needs to improve. Slowly we are moving from the old systems to the digital systems. Infrastructures are being renovated to cater to the IT/OT requirements, IoT requirements, and the power infrastructure is undergoing a transformation for the last few years. And many smart meters and automation systems and communication systems have been added in the distribution segment as well, SCADA, DMS, and of course, transmission they already have. So what I want to emphasize is that digital transformation for the infrastructure and particularly power in India is in the, I can say that in the nascent stage, and we are going at a very high speed to convert the existing system into a very responsive digital infrastructure. And today's lecture basically will, by Dr. Giovanna and her colleagues, will be covering as to how this digitization will put the world into another type of problem, which is cybersecurity or the cyber threats. So how to protect the power system from the cyber threats, what needs to be done, how we design our cybersecurity infrastructure, that is important. And at the same time, we need to really understand that a planned approach, strategic approach towards implementation of the cyber infrastructure is necessary. And we need to really make our funds available for cybersecurity now, because world over the cyber threats are increasing, and naturally the power sector being infrastructure, critical infrastructure in India as well, it is most vulnerable. And we need to really see that the power sector is not attacked by the hackers or any people who are trying to damage our system or do problems with the ongoing operation systems. So I will now request Dr. Giovanna Dondosola to kindly take over and deliver her lecture along with the colleagues. And we all look forward to hearing them. And thank you again, Dr. Giovanna and your team, because you are joining in the early morning. And we hope that it is not put you under a lot of inconvenience. Wish you good luck and a good seminar we are expecting from you. Thank you so much.
Thank you so much, Sudha, for your address. Now, before we hand over to the presenters, I would like to give you all a brief introduction about our eminent speakers for today. First of all, I would like to greet Dr. Mauro also. He has just joined us. Dr. Mauro, welcome to the program. Now, ladies and gentlemen, we have three eminent speakers for today's program. Dr. Giovanna Dondosola received her MSc degree in Information Science from University of Milan in 1987. She is currently leading scientist at the Transmission and Distribution Technologies Department of RSC, Italy, where she technically leads national and European projects on the evaluation of cyber risks in smart grid communications. She is responsible for RSC TCS RES test lab for the power control system resilience testing. She She has been an active member of SIGRE working groups on cybersecurity, and currently she is the chair of the advisory group D2.2 on cybersecurity. She is the secretary of the Italian National Committee 57 of CEI, a member of Working Group 50 on Data and Communication Security within TC57 of IEC, and member of CEI CT313, Italian Mirror Committee of IEC on Smart Energy. She has also co-authored hundreds of publications on electrical control systems, cybersecurity, including papers, articles, and chapters in international conferences, journals, and books, and has made several speeches and lectures at panels, tutorials, and training courses for academies and utilities. Thank you, madam, for joining. Now, our next eminent speaker, Dr. Roberta Terrugia. She obtained her PhD degree in computer science from the Doctoral School on Science and Advanced Technology of University of Turin in 2010. She is currently a researcher at the Transmission and Distribution Technologies Department of RSC Italy, where she is involved in national and European projects on the cyber security of energy grid communications. Before joining RSC, she had been postdoctoral fellow at the Computer Science Department of the University of Eastern Piedmont in the Computer Systems and Networks Group. Her current research topics cover studies on cyber power risk analysis and cyber security preventive and defensive measures for digitalized energy. She is currently a member of TC57 of IEC, Working Group on Data and Communication Security, Working Group 10 on Power System IID Communication and Associate Data Models, and Working Group 17 Communications System for Distributed Energy Resources, and of CT57 of CEI. She has also authored more than 50 publications and lectures in international conferences, journals, books, and courses. Thank you, Dr. Roberta, for joining. Now, our last speaker is Dr. Mauro G. Todeschini. Dr. Todeschini obtained his BSc from University of Milan, Bicocca in 1999 and MSc from the University of Milan in 2008. Since 2000, he has been in charge of system and network management of public internet services with particular interest to cybersecurity issues and solutions. Since 2009, he has done research in the field of virtual reality for industrial applications with focus on networking and data communications issues. Since 2017, he is researcher in RSCSPA and ICTC57 Working Group 15 member, where he develops solutions for the evaluation of the cybersecurity measures applied to power systems. Thank you, Dr. Maura, for joining us. Ladies and gentlemen, these few words cannot justify the amount of experience our eminent experts has, but I assure you all are in great hands for this tutorial. Now, without wasting any more of your time, I would like the speakers to take over with their presentation, please. Dr. Dondasola, over to you.
Okay, thank you. I will try to share my screen for the presentation. Please let me know if you can see the screen properly and also if you can hear me.
Yes, ma'am, your presentation is visible and you're audible. Okay,
thank you. So thank you to all for this kind invitation. Thank you to Olga, but thank you also to SIGRE India and Mr. Soda for the kind words introducing our activities. And we are very pleased to be here today with other colleagues in RSC. RSC stands for Research for Energy Systems. So it's a research company. So can you see the slides, please?
Ma'am, we can see your screen, but you need to open the first slide to full screen.
Unfortunately, it is in full screen in my laptop, but let me check.
Yes, ma'am, we can see the full screen now. Ma'am, kindly unmute yourself, please. Ma'am, you need to open the Microsoft Teams and unmute yourself from there.
Now we should be ready, right? Can you see the screen now? Okay.
Yes, ma'am, we are good.
Okay,
Yes,
thanks. I was just saying thank you.
Not yet, actually.
It's my humble request to all the participants to kindly keep yourself muted. In case there are any queries, kindly post them in the chat box. We'll take all the queries at the end of the presentation. Please avoid providing any disturbance to the presenters. Ma'am, you're good to go.
Okay, thank you. Thank you for this opportunity to present this tutorial today. RSE stands for Research for Energy Systems. We are a research company based in Milan, Italy, and we are basically carrying out applied research to the value chain for energy systems, starting from market models and system level scenarios development, but also studying the environmental impact of energy systems, moving towards technologies, transmission and distribution technologies, material and generation, and in particular, our activity is with the Department of Transmission and Distribution Technologies, and all the three speakers today belongs to the ICT activities that are in charge of this department. And just moving to the table of contents and the different sessions that you will hear today. The tutorial is structured into three main parts. In particular, I will introduce and provide an overview of cybersecurity in power systems in considering the evolution of cyber threats and also what is the key issues in energy transition that we are dealing in these decades. And in the second part, session 2, we will move towards more specific technologies, in particular cybersecurity for telecontrol protocols that are used for the observability and controllability of the smart grid. And session 3 will complement the technologies by explaining and showing platforms that are specific for monitoring and anomaly detection with experimental setup that we have in our labs here in RSC that are related to the new and emerging technologies in terms of IoT platforms, but also platforms that are more traditional and based on wired or wireless communications for DR control and monitoring. And the third session, the last session, is about the activities that is performed within SIGRE and SIGRE Study Committee D2 that has already been introduced by also by the chair of SIGRE India. So just let me start with the first session. So I like to introduce cybersecurity and the needs for cybersecurity in the power sector, starting from the energy transition, because all over the world, actually, but in particular, I'm presenting the European picture. We have, and the European Union has published a Clean Energy for All European package document that establishes which are the targets in terms of renewables energy and also energy efficiency for 2030. And as you can see from the slides, we have 3 main targets established in this European package. And in particular, we have 30% cut in greenhouse gas emissions compared to 1990, 32% share of renewable energy, and 32.5% energy saving compared with a baseline scenarios that has been established for this study. So what this means? This means that digitalization and digital technologies are key enablers technologies for this energy transition, because we need to connect different and heterogeneous power plants that you see in the left side of the slide with the power grids, but the main goal is to optimize such amount of power with also by managing different kind of flexible loads in terms of course, industrial power plants, but also commercial and residential buildings and also EV charging. So we have the needs for improving the efficiency of this extended infrastructure, power infrastructure, and for sure, digitalization provides both technical and economic objectives, because in terms of technical objectives, we have, of course, digitalization as the possibility to improve the quality of data exchanged between the different operators, in particular distribution and transmission operators, but also with, as we said, significant grid users. And so we'll be able to provide faster and more efficient services to the different stakeholders of the picture. Of course, we have the ability to connect different kinds of generators and facilitating also energy management in this side, and to promote demand side management, so the controllability of flexible load in order to exploit at the maximum extent possible the flexibility available also in the load side, in the customer side. And then we have also technical benefits for sector coupling, because we are not only speaking about electricity sector, but of course we have to reason in a more wider multiple sector view, including also, for instance, the gas sector and for sure the heating sector, and combining the different transport and the EV charging, combining the different sectors for a wide picture and optimization. And finally, we have also to integrate storage systems and to have such renewable generators that are whose behavior and production is optimized thanks to the presence of storage devices that can, of course, complement the instability or uncertainties that is typically intrinsic in this kind of renewable generators. So from the side of cost reduction, we have the possibility with digitalization to improve the productivity of the different power plants, because with this availability of data, we can have enhanced forecasting and smarter control of the power plants. We can reduce the operational cost and the capex cost, the investment cost, thanks to availability again of data analytics that can improve, for instance, the maintenance activity on the power systems. And from the side of the capex cost, we can reduce investment thanks to the optimal usage of available resources. We can extend the lifetime of the devices by appropriate maintenance plans, and we can, of course, improve also the values of power in somehow, so the values of the megawatt hour produced, because we can have efficient trading systems that support the markets. So in terms of how the standardization is moving in the international landscape, I do like to reference to this report that comes from the International Electrotechnical Commission that introduces a conceptual model of smart grids. And as you can see, we can have different kinds of users that we already mentioned that are managed by different kinds of actors or operators. We have smart grid operations in orange on the left side, but we have, of course, also metering operations that are on the right side. And in the middle, we have operators of energy services that are new, let me say, in the picture, because we have new markets that are able to manage aggregated resources, both in terms of generations and load. So in terms of architecture, we have here in the picture a view that is a mapping on the smart grid architectural model that shows that the architecture is very distributed and in particular is very populated in, if you see in the DR and customer domain, with several kinds of controllers that belongs, of course, to different customers. And these devices and controllers are controlled by higher levels and centralized systems that may be located at different levels of the control hierarchy here, as you can see. So, of course, this means that we have a control infrastructure that is quite hierarchical and distributed, and different actors are interfaces to the control devices, and through, of course, specific technologies in terms of communication and also elaboration platforms. And we have, in particular, also a parallel, let me say, phenomenon that is going and upcoming together with the energy transition. We have the digital transition. So we are experiencing, as we mentioned, new emerging platforms that are that can provide some, of course, advantages also to the different services of the energy systems. And we will see along the tutorial how they can be introduced in terms of observability and controllability of the whole system and infrastructure. So all this introduction, of course, is for setting up the scene for cybersecurity, because as you can understand, the attack surface in terms of possible threats that can compromise or disrupt, in the worst case, the behavior of the power systems is increasing. And here you see that the different kind of attack groups are, of course, also increasing along the time. And they are targeting the energy infrastructure by using different kind of skills and improving their knowledge and competence and abilities in terms of capabilities of reaching the critical device and compromising the critical services. So what is clear is that the introduction of distributed energy resources along the power systems increases the attack surface, and so we have different kind of DR threats that may be successful at the different level of the control hierarchy, as we can see here in the picture. And of course, we need to introduce cybersecurity measures in order to mitigate the effect of such successful threats. And they have different kind of maturity in terms of DR. And so the current status, and I will mention which are the most relevant standards for this domain. And the current status is that we need, of course, to integrate the best solution available at the different levels of the control hierarchy. And in terms and moving towards emerging technologies, the picture is even more complicated, because we know that such platforms have different levels of let me say, of application. So we can start from the very low level, from the single devices and single sensors that are able to provide also power measures in some cases, moving towards the ICT infrastructures that relates to communication devices and elaboration data centers, which may be located at the edge or what is called also fog computing, at the edge of the infrastructure, or at the more central levels by using cloud-based platforms and services. So this means that at the different levels of such platforms, we have to identify the potential security weaknesses that are somehow new weaknesses that comes into the picture, and that have to be considered in terms of availability of resources, but also management activities and different, let me say, level of policy engagement in terms of cybersecurity in these different areas. So I think that giving this kind of picture, it's clear that the energy sector needs to have a well-defined regulations that deals with cybersecurity and exploiting available standards. So I will go through the key kind of regulation and standards that are referenced in around the world. And eventually you have also references that, and you can ask if you need details, because the picture is quite comprehensive. I want to mention the NERC standards, that is the first series of standards in US that has been developed since 90s, and in particular, we have different kind of chapters of this kind of standards dealing with the different aspects of cybersecurity. And you see from security management controls towards electronic security perimeters, but also incident reporting and response planning and the recovery plans for bulk energy systems. That is the main focus of the CIPS standard. And these standards are continuously updated, and you see from the picture that is very updated that we have several parts of the standards that are subject to enforcement in these years, and others in what we have in the last part of the slides that are still pending for approval, and they are related to new version of these chapters. So this means that in particular, you see that electronic security perimeters and also supply chain risk management is going to be updated. So these are the key topics introduced, and at least the key topics that has to be included in any information security management system. And moving to Europe, we have the NIS directive that has been published in 2016. And in particular, this directive and the Article 14 that you see on the slide is specific for security requirement and incident notification for operators of essential services. So this means that such operators has to take appropriate and proportionate technical and organizational measures to manage the cyber risks. And of course, they have to prevent and minimize the impact of such incidents. They are also asked to notify without undue delay the competence center that are the so-called cybersecurity information response teams of incidents that have a significant impact on the continuity of their essential services. So what is very explicit in this regulation is the need to notify what is going on, what is considered critical for, of course, for the most important business processes that have an impact also potentially to other infrastructure of the nation, of the different member states in Europe. So in order to tackle with all these issues, in Europe, we have network codes that are specific rules that harmonize, let me say, the management of the power infrastructure, and in particular the electricity sector. Such rules are defined by ENTSO-E, that is the Association of Transmission System Operators in Europe. And they are grouped, as you see, in different kinds of families of network codes, but all of them are related and require data exchanges for being implemented. And in particular, in the operation family, you see the operations that includes, in particular, a network codes recently published that defines which are the requirements for data exchange between TSO, DSO, and significant grid users. And what is moving into network code is also cybersecurity. So we are in the process of defining, we in Europe are in the process of defining a specific network codes for cybersecurity, where an informal process has already started for deriving recommendation for such a network code. So we have a group of transmission system operator and distribution system operator defining this recommendation. So you see that the structure of the network code is divided into different topics, and in particular the first one is related to the identifying the cross-border cyber risks. That is, of course, related to the interconnection between the different power system along the borders of the member states, and of course also the needs of defining common security controls and requirements. So having a baseline of requirements that are met by all the member states, and in particular related to the most critical risks on cross-border relationships. And we have also the need of defining product assurance schemes. So, of course, to develop appropriate schemes for certifying cybersecurity of the different products used in this domain. And from the side of individual TSO and DSO involved in these activities, we have, of course, the requirements for them, for the most critical companies, to be certified according to the IEC 27 standards, 27 key standards. So I will mention something later about these standards, but very, very briefly. So I think that, of course, you see that finally we need to have also sharing of technical information. This is very, very important for managing the new threats. So we and in particular, this group is perfectly aware of the fact that threats are evolving in time, and there is the need to, in order to be very proactive and for mitigating the upcoming malware and the upcoming anomalies, it's important to have this information very timely. And this is also the scope of the warning systems and the information sharing systems and organization that are taking place. So moving towards certification, and in particular, we have a certification process that, of course, requires to have specific bodies that are accredited for doing such kind of certification, and also people involved and auditors involved in the process of the certification has to be certified themselves. So we have a structural process for performing such kind of certification, and for in particular identify specific centers that are accredited for doing that. Moving to standards, I mean, the picture of standards for cybersecurity, I think, is very well presented in this report from the IC System Committee, Smart Energy, and the Cybersecurity Task Force. I just will mention the key point of this guideline, and you see that there are 5 main key principles underlying cybersecurity in power systems. And the first one is that cybersecurity is very, very related to resilience of the power systems. So it's one line on defense now, because systems are fully digitalized. And so we need, of course, to see cybersecurity as part of the resilience framework of this whole system. Then we have security by design as a principle that has to be applied during the system development. We have the different characteristics of information technology versus operational technologies, and risk assessment is a key pillar for managing the cyber risks. So there has to be a risk assessment methodology in place in order to manage and along the life cycle, the evolution of risk and security measures. And of course, we have to be supported by appropriate standards and guidelines, which are very relevant for managing and dealing with cyber risks. So the relationship between cybersecurity and resilience, I think, can be identified by specializing this kind of definition that comes from CGRE Working Group C447. We also have a very brief paper published around this link. And in particular, what I want to underline is that cybersecurity is something that comes with, of course, the behavior of the system along the time. So there have to be key actionable measures also in terms of cybersecurity that applies before, during, and after a specific cyber events. So in the same way in which resilience is tackled in terms of different kind of extreme events in power systems, as we have here in C4, we have to apply a similar approach to cybersecurity by considering actually the the time evolution, so that the time dimension of cyber threats. So that is the key point. And here you have an overview of the reference standards for that the group has identified as very relevant for the energy systems. Some of them actually comes from the IT domain. Some others are more related to industrial control systems. So you have here a very comprehensive view of the standards. They are structured in terms of organizational and technical standards, and also document that support certification and compliance. One of the, let me say, reference standards or framework for cybersecurity is the NIST framework for resilience that identifies 5 key functions that has to be included in any kind of cybersecurity program. And these functions are identify, protect, detect, respond, and recover. And each of these functions, of course, is associated with a set of specific, more specific categories of controls that you can see here in the picture. So this is the way of structuring, let me say, a full comprehensive program for cybersecurity. In the same way as is done from the series that I mentioned, that has been already mentioned also by the work on the network code, that is the 27000 series. And in particular, there is also this part 27019 that is specific for energy systems. So here you see that the different categories or classes of activities are included in the structure of the report. And in particular, a set more than 100 set of controls are defined totally. And you see from the dimension of the slots, which are the most populated categories of cybersecurity issues in terms of controls included. And another standards that is specific for smart grid is not a full standards, it's a guidance. It's a guideline that has the peculiarity, in addition to defining again categories of cybersecurity topics, has the peculiarities to identify a methodology for automatically associating security requirement to specific communication interfaces. And this methodology is based on this logical reference model defining the standards, and according to the different interfaces that are of interest for a specific application, it is possible to derive a predefined set of requirements that are relevant for that interface. So I think that even if the logical reference model is not complete in terms of all the kind of applications that we can have, the methodology is valid in general, so as a general validity, and may be applied for deriving security requirements. And finally, we have this standards 62443 coming from the industrial control system domain. And here again, we have peculiarities in the standards because there are requirements related to the development life cycle, so that are specifically related for vendors and integrators for checking their development processes. And then we have requirements that are for the components and the systems. And in particular, the key point is the definition of security levels. And I think that this concept of security level associated to system and then to components is quite key for deriving the appropriate solutions for the level of security that is required in a specific system or domain. So finally, we have you have a set of references that have been mentioned during my presentation, and in case you need, they are all available. I mean, all of them can be downloaded from the network. Okay, so now if you have some questions, I'm happy to answer. Otherwise, we can move toward the second session. So I hear no questions, so I think I can stop sharing and give the floor to my colleague Mauro Todeschini.
Okay, thank you, Giovanna. I'll try to share my screen. I'm sharing the screen, and please let me know if you can see it so that I can start my presentation.
Yes, sir, your screen is visible.
Okay, thank you very much. Thank you, Giovanna, for your introduction. And also thank you, organizers, for letting me present this presentation and speak about my research topics. And good afternoon, everybody. In this presentation, I will talk about some well-consolidated cybersecurity protocol, or let's say some protocols that to protect the communication that happens during a telecontrol of mainly distributed energy resources. The contents of the presentation are this one. Talk very briefly about the power system evolution that and the new needs that are emerging in this telecontrol because of this evolution. I will talk briefly briefly about some threats that may happen in or cybersecurity threats that may make problems to the telecontrol. And I will talk about which solution are foreseen in IEC 62351 standard, concentrating in particular on the TLS solution, which is a protocol that is very well consolidated, not only in the power system, but also in other sectors. And think about financial sector, or also messaging sector, and a lot of sectors, let's say. And I will say, I will present what are the benefits that the TLS introduces with a very low, let's say, impact, negative impact in performance, and also in the difficulty to implement it, because it's a very consolidated technology that nowadays can be implemented quite easily. So let's proceed. Here you can see in a very schematic way what's the evolution of the power system nowadays. We are moving from a, let's say, small number of big plants, mainly using fossil energy sources, to a cleaner power system which sees the use of renewable energies like wind energy, or also solar energies, photovoltaic solar energy. And instead of having a small number of big plants, we are moving to a very high number of smaller plants that are usually owned by different subjects, and so they are managed in different ways. That's the reason why telecontrol or remote control is gaining more and more importance, because we now need to cope with different ownership, different systems, different technologies, different products, and we have to manage them in a very coordinated way, because we need to keep the system stable and efficient. What's telecontrol? Simplifying a lot, we can think of being able to understand or measure the performance of the distributed energy resources, getting measures about their performance, the energy that they introduce in the system, and also being able to control these sources. So, for example, to reduce the energy that they are introducing to the system, and maybe also deactivate or activate some resources if the stability of the power system, or also the requirements of the industrial and of the society requires them. What do we need to do this telecontrol? Well, for telecontrol, we obviously need some communication protocols that let us control the resources which are distributed, highly distributed in the country, in the environment, so that we can control from a centralized control center also resources which are very, very far from the control center. And to do that, we usually use protocols which are mutuated from the internet nowadays, because they are very well consolidated, they are very well tested, and they are very well, let's say, reliable. Here you can see a stack of protocol, the typical stack of protocol of internet Internet protocols, where you can see a physical layer, network layer, and transport layer, and application layer, and each layer gives services to the layer which is upstairs. Our measures, our set points are transmitted in the application layer, which uses protocols which are specific for the power sector, such as IEC 61850. You can think about MMS, the very well consolidated protocol for the distribution system, or IEC 60870. Even you can think about the protocol IEC 104, which is also very well consolidated. And but the application layer, this kind of stack is not only specific to the power system, but regards every communication in the internet, such as you can think about HTTP, which is the protocol that is used to transfer the web pages that you can use for accessing the internet. What happens in reality is that in a data channel, all these protocols are encapsulated one in the other, and a sequence of packets is transmitted in both ways. So if we think about the telecontrol of the distributed energy resource from a control center, we can see that the measures usually are transmitted from the distributed energy resource to the control center, which responds back with set points for applying corrections to this to the behavior of the distributed energy resource. So we have a sequence of packets that travels on the network in both ways. What's the problem of this technology, of these solutions? The problem is that these protocols were developed many years ago, and as they were developed, they are not resilient against a number of cybersecurity attacks. Here we can see one of the most, one that can, let's say, usually quite easily be actuated, and one that is not, which the protocols we have talked about in the previous slide are not resilient to. You can see that a hacker can gain control of a device which is on the path of the communication. You know that the internet is a collection of nets, so the communication travels over different networks, passing by different devices, usually routers. And if an hacker can gain control over one of these devices, it can also modify the traffic that is passing by, or see the traffic. Maybe the traffic can contain relevant or confidential information that people don't want to share. But if the attacker could also modify the traffic, he can, let's say, for example, change the order of a control center to reduce production in the order to increase production, producing instability of the system, or also faults, or also problems to the power system. So this is what we want to prevent. And how can we prevent this? Well, there is an international standard, which is IEC 62351, which lists, reports a lot of solutions that can be applied. And this solution are solutions that can be applied to different layer of the protocol stack that we can see on the right, or also to different protocols at the same level of the stack. For example, there are parts of the standard which refer to MMS protocol, or parts of the standard which refers to, for example, 104 protocol. Or also there are parts of the standard which refer to network or physical layer security. In this presentation, we will concentrate mainly on the solution that we can see here at the transport layer, which is called TLS, because this is one of the most consolidated, readily available, and also which has very good performance. Here we can see how TLS works. It is a protocol that works mainly at the level of transport layer of Internet Protocol Stack. That's why of the name. TLS stands for Transport Layer Security, and so it protects information that are at the layers above it. So it's the right place to protect information that are related to the telecontrol protocol, so set points and measures. And how does it protect them? For example, encrypting this information so that the hacker before cannot understand the information, and so it's much more difficult for him to change the information. To be honest, it's impossible for him to change information because TLS has a lot of benefits. One of which is, for example, authentication, which guarantees to the party, to the DAR or to the control center, that the information is sent exactly from the control center or DAR and not from an entity, a subject that is in between of the communication, such as an hacker. And then it has also another very important benefit, which is integrity, that guarantees that information is not changed in the path, even if we don't encrypt it with other techniques. Now we will see. Now we will. So the main benefits of TLS are this one. Let's talk them again. Confidentiality regards the possibility to prevent unauthorized parties from accessing the information. Authentication is about ensuring that a message was created by a particular party, such as a control center or DER. And integrity regards the possibility to understand if the information is changed in the path. The parties, the elements of cryptographies are this one. So there are the parties in communication, which are in our cases are DER and control center. There is the messages that we want to transfer. If we encrypt them, we call this information ciphertext. While the information, when it is still not encrypted, we are referring it to plain text. In our case, they are set points or measures. Then there are algorithms. For example, there are algorithms that regards encryption or decryption of the information, but also there are algorithms for the signature of the information to guarantee the source of the information. And there are keys, which are passwords. There are two main systems about cryptography and keys. The symmetric system, which uses a single key for a single communication, or there is also the asymmetric cryptography system, which uses two keys and is very good for channels which are not secure by default. Here we make some brief examples of the two systems. Here for the symmetric cryptography, there is the same key that you can see on the left and on the right that is used for encryption and decryption with two different algorithms, one for encryption and one for decryption. So the problem, this system has benefits and problems. The benefit is that it's really, really fast. So there is no big impact in using this kind of cryptography to protect information, but it has a let's say, problem, let's say requirement, which is quite important. That the key are distributed in a secure way. So here we can see that both parties must have the key. And so there is the phase of transferring the keys, communicating the keys is very important, and cannot really be done on the internet channels, internet protocols, because they are subject of the attack we have seen before, which is called man in the middle. But if the keys are distributed safely, this is very secure and can provide confidentiality. There is another system which is called asymmetric cryptography, which has the problem of being slow, but is very resilient for the use with unsecure channels. If another technology is used, which is the technology of digital certificates. In this case, we use not only one key, which is not only the private key, such as the previous system, but also another key, which is which has fewer requirements of security and can be distributed easily on an unsecure channel, which is the public key. And the public key, both keys are used for encryption and decryption. I will not enter in the details here because it would take time. But let's say that this system has the benefits that we don't need anymore a secure channel for key distribution. But we need digital certificates, which are, let's say, an association between an identity and a public key of a subject. So we will have a digital certificate for distributed energy resource, and also a certificate for the control center, which is both of the parties which are communicating. And these certificates can be obtained by third-party societies, companies that does exactly this work of associating and guaranteeing this kind of association. TLS uses both of these technologies, asymmetric and symmetric cryptography. Why? Because it uses asymmetric cryptography to distribute the keys of symmetric cryptography over unsecure channels. So this work is corresponds to making the communication channels secure. When the keys are distributed, when the symmetric keys are distributed in such a way, symmetric cryptography can be used because it has no more any problems with security. So we can gain the benefits of being of a very fast communication after this initial handshake, which is used for transfer of keys. The first part usually is very limited in time because it only needs it is only done for transferring the keys, and the second part is very maybe longer because it where measure and set points are transferred. Parameters of TLS that IEC 62351 specifies mainly the cipher suites, which are the algorithms that are used for key transfer and for cryptography. And the let's say length of the password, we can think of it's the length of the keys that are used for the encryption phase. So a higher length keys corresponds to higher security, but the standards let you use also smaller keys, mainly for backward compatibility reasons. So the standards let you use also 1024 bits keys. And the cipher suite name is divided in three parts. The first part, which is about the symmetric keys generation and transfer. The second part regards the encryption, and then the third part corresponds to hashing, and so integrity verification of the communication. Here we can see the results of work we have done to show how much is the impact of TLS over the communication. Here we can see that the handshake phase, which is the phase of the communication, may take also about more than 400 milliseconds, which is a lot if you compare to 1 millisecond of not using TLS. But as you can remember, this impact is only in the very beginning of the communication. So this is not a real high impact on a telecommunication, telecontrol communication. Here you can see also that the impact depends a lot of the key generation and transfer protocol, and also on the key length. So, which is about it, but doesn't regards a lot on encryption protocol. Here instead, you can see that the impact on measure and set point transfer is very low. On this part of the slide, you can see that when you don't use TLS, you gain only less than 1 millisecond over a single measure transfer. So the impact on this phase is really, really limited. And this is not so much dependent on a key length or the protocols used, because this part uses symmetric cryptography, which is very fast and very efficient on modern nowadays hardware. As coming to the end, I just want to talk about how much secure are these protocols. Let's say that here are two examples of how much time it would take for an attacker to break these two kind of technologies, these two kind of cryptography. For symmetric cryptography and for IC25C algorithm, which is a very diffused and used algorithm, for an attacker it would take about 10 to 60 years to be executed on a single PC, which is more than the age of the universe. And even if an attacker that could begin use of all the PC, all of the world, it will take also more than the age of the universe many times. This kind of algorithm is very secure. In the case of asymmetric cryptography, you can see that for shorter keys, it was already possible in the past year to break the security, and that's why 104 length keys nowadays are not recommended by the standard, because we think that that kind of keys will be break in the next 10th of years. But if we use 2048 and 3000 bits keys, surely we will stay secure for many years to come. So for the conclusion, we can say that cyber attacks are a real threat for the power system, because the protocols used are not resilient as they are to the cyber attacks, but they can be secure. But using solutions such as TLS, which is already consolidated and widely available. There are open source software libraries to implement them, and so they can easily be applied. TLS is optimized both for security and for performance, thanks to the fact that it uses asymmetric cryptography to make the channel secure and symmetric cryptography to make the communication fast. But the standard that we talked about before, IEC 62351, also suggests other solutions that can further raise the security, network level, or advance at the physical layer, and also to solution at the application layer specific for 61850 protocol and 60870 protocol. What's important is that this solution is better considering the design phase of a solution and not as a emergency solution to be applied only when a problem arises, so that you can evaluate specifically which parameters and which solution are best for your scenario. I think that's all. I hope not to have been too long in my presentation, and these are some references to the work we have done in the recent past, and I have briefly introduced before about the performances of a cybersecurity solution based on TLS on widely used protocols in the power system. Thank you very much. And is a question, I will pass the presentation to my colleague Roberta. Okay, I think I cannot hear anyone asking a question, so I will pass the presentation to Roberta and stop sharing.
There is a question, Mauro. There is a question on the chat.
Just a moment. I will try to see what is the chat. So I see the. I think that the question is, any additional equipment units can enable the cybersecurity function, or it can be given as inbuilt function with the IED? Okay, this is quite an important question. Thank you for me asking it. We are working in work group of 15 of the IEC of the technical community, and these solutions are in the course of being introduced in the devices, in the IED, and so on. I cannot guarantee at this moment that every model of the you can find already includes all these solutions. What it is important is that, in my opinion, DR starts asking this solution to be readily available from the producers when they are going to upgrade their infrastructure, their technologies, and so on. Because the standards are already available, and so the producer are already, let's say, enabled to provide many of the solutions I was talking about. What's important is that, let's say, the operators in the system would ask devices that already implement them, so that they don't need to introduce use other technologies, external technologies. I cannot guarantee that these solutions are already implemented, but they are in the course of our implementation, so you can already ask them. So there is another question. For providing web access of a plant SCADA data through internet, what are the special provisions to be considered in the design for avoiding cyber attacks? Web access may mean, if you mean, let's say, access through the internet, because sometimes web think about HTTP access, or sometimes you can think about accessing through the internet. In my opinion, of course, TLS is a solution that is readily available and can be applied right now. But of course, I usually suggest not to use a single solution, but to cope with a combination of solutions. Another very important solution that can be applied and gives more reliability is, of course, the solution of implementing VPNs when it is possible, and usually it is possible in our system, which are a solution, and they are a very consolidated technology, so they can be applied right now. And I know that of many DSO or TSO that already implements and require them, so they surely have to be implemented. And then also the local network of the TSO, DSO of the production plant must be considered. And so you have to consider also the security, segregation of the traffic, and the security of the systems in the local network. So there's a lot of points which an hacker can attack, and so there is a lot of technologies that must be applied in order to keep the system secure. I hope to have answered your question. There is another question, which is another very interesting question. Any modification in the key after some interval could reduce interference? Yes, of course, and the standards already. Of course, the key is like a password, so it's a good behavior not to keep a key, use the same key for a long period of time. But the standards also specify which are the intervals of changing keys, which refers mainly to the keys which are generated in the first part of the communication, of the TLS communication. So the standards says that the key must be renegotiated every specific amount of time, which is configurable, and there are rooms in which an operator should stay. So they have to stay in the intervals are about hours of length. So you have to renegotiate the keys every at most 24 hours, for example, or at least some minutes or something. I don't remember exactly the minimum interval, but is about minutes. So the standards also specified which are these intervals. Can hackers fake digital certificates? If so, what are the mitigation techniques? Of course, this is another very good question. I have not entered in the details here because it would have taken a lot of time. But of course, also in asymmetric cryptography, the user, the part of the communication, must keep the communication, the private key very secure. This usually can be done because in this case you don't have to transmit the key on the network. So it can easily be done. But if you are talking about certificate, yes, the certificate is important to be secure, because it copes with the authentication of the communication. So if an hacker can get a certificate, but it must also have not only the certificate, but also the private key, which is not easy to get. It can also impersonate another part. So yes, the certificate must be, let's say, it must not be kept secure, but you have to check that the information in the certificate is correct by using the public key infrastructures, which can easily be done. So that's why we have to also on the side of certificates there must be some attentions. I cannot see. Thank you for this very interesting question. All the questions were very interesting. I hope to have answered. But if there are no more questions, I will let the word to Roberta, which maybe has also a quite interesting presentation.
Sorry for
Thank you very much.
Okay, thank you for the flow. Now I try to share. Okay. Do you see the slide? Okay, perfect. So now in this part of this tutorial, we move on the emerging technology for the energy systems. In particular, we see some platform for preventive and defensive security measures, and we see some experimental setup. So we see that the emerging technology could provide important aspect for the energy digitalization. And so we see that we need some platform in order to implement preventive, so in order to secure the real network, the communication real network, but also for defensive, so for monitoring and anomaly detection. So we see some emulation of cyber attack, some platform for the collection of events, and then some techniques for the detection of the anomaly. Then we move on the experiment setup, both for preventive and defensive security measures, into special setup. The first one is typical for emerging technology. So it's about the secure IoT and cloud-based infrastructure for monitoring power consumption and asset controls, particular with focus on electric vehicles. And the second one is more classic, more traditional, is about the distributed energy resource monitoring and control. Okay, and then we conclusion. So the new information and communication technology help to improve for the evolution of the power infrastructure. In particular, we have new actors and functionalities, as for example, electric vehicles, demand response functionality, the actors related to significant grid user, and so on. In particular, in the context of energy system, emerging technology can be applied in two different ways. For new functionalities, or in order to rethink some traditional, for example, power and monitoring control functionalities. But all this is for all this is important, the cybersecurity, because the attack surface is wider. What's happened? Okay. And in particular, because the electron energy infrastructure are target of real-world attacks, as we see in the previous presentation. So we need to study the cybersecurity. In particular, we focus on emerging IoT platforms. IoT platforms are composed by different layers. So we start from the sensor, the actuators, the device at fit layers. Then we can have some way a gateway, edge layer, and then this data could be sent to cloud for more application and elaboration. So we need to implement cybersecurity in order to protect all these different layers. So all the processes of the data from the sensor to the cloud from the higher levels. So for study this aspect, we implemented a specific infrastructure where we have different IoT devices that send information to edge gateways or Fox nodes, and this is interact with a cloud platform based on OpenStack. This cloud platform is a private cloud, but it is a private, but also a public, because we can use both cloud, but also the public platform, in order to perform ICT analysis, but also power analysis or cybersecurity task. So we need to implement security at the component layer, for the communication, and at the application level. Particularly, it is important to things preventive, but also defensive security, because preventive, so we implement measures in order to prevent that the attacks occur, are not enough, because some also the TLS, the password, all the solution could be in some way we can go on, and the attacker can use some weakness in order to perform an attack process. So we need to implement some solution in order to defend, so intercept the evolution of the attacks and stop and provide some remediation. Okay, so as some example of preventive measure could be, as we see, the TLS, but also at application level some way to allow the integrity, the confidentiality, and the availability of the communication. So we have some standards that are specific for the power telecontrol protocols, but also standards and guidelines that are specific for IoT, for emerging technologies. So we need to implement the solution that are used and can be applied for the specific platform that we address. Moreover, we needed to perform some intelligent threat analysis. In particular, we need to analyze the vulnerability, the threat that could occur in our platform, and implement a monitoring real-time monitoring in order to collect events that could be analyzed, and in this way we are able to perform some remediation actions. So for the detection, the process for the detection, the response are based from the identification of evidence that could be monitoring values, but also logs or any information that could be of interest for security task. Then this evidence needs to be collected, for example, with SNMP, syslog, or specific protocols for the collection. And these protocols need to be secure. Then we need to correlate and analyze this information in order to detect anomalies perform alerts, and then deploy prevention and recovery actions. So in our laboratory, we have implemented a monitoring platform that is based on SNMP and syslog, and implement indicators, general IT indicators, so general IT device information, but also typical of the power context. In particular, we also have been a contribution for the development of the 62351.7 part for the monitoring and 62351.14 for the log and the event collection. So we have implemented this platform in order to collect information. We have the data. We need some some techniques for analyze and detect anomalies. In particular, we need some automatic techniques that we see that we use some artificial intelligence techniques in order to provide alert and detect anomaly. So, as I see, we have a machine learning techniques that will be used for anomaly detection. So we start from the analysis of attack process. We say that the attack process is not an atomic step, but is composed by sequences of different steps. So we need to use the monitor platform in order to collect informations. And so we apply techniques related to machine learning, deep learning, in order to identify malicious anomaly in general, but particular malicious anomalies. Okay, so here we have some results about our techniques applications. Okay, now we see the implementation of two experimental platform where we have implemented the platform preventive and defensive platform. In particular, the two different setups are related to secure IoT and cloud-based infrastructure for monitoring power consumption and asset control, and distribution energy resource monitoring and control. So we have that the evolution of ICT architectures move on with IoT, fog, edge, and cloud paradigms. So we need some solution that provide security, but that need to be cost effective, because in several cases the implementation need to be implemented in, for example, in a house, in a very wide area. So we need to also consider the cost. So in particular, we focus on the architecture for the monitoring and control of electric vehicle recharging system. And we see how the security measures impact on the performance and on the implementation of this infrastructure. In particular, with the increase of the number of electric vehicles, it's very important to develop a solution for the control and monitoring of home recharging systems. So in this platform, we focus on the application for the acquisition of charging profile of residential customers that have in some way electric vehicle charging stations, so in home stations. So we have the power infrastructures, but also an ICT infrastructure with some smart node connected with cloud that could be remote applications. Particularly, the ICT architectures is composed by several IoT sensors that communicate by means of a Z-wave network with some single board computers. some Raspberry, for example. In our case, there are some P4 Raspberries that are able to communicate by means of a wide area communication router with our private cloud by means of MQTT protocols. So in this picture, we see the different components, hardware components of this infrastructure. We have the Raspberry, the sensors, the routers, and so on. Here we have another picture of the architecture of the infrastructure that we've implemented. So we have the Z-Way communications. We have the Open Hub that collect and provide MQTT communication to a broker, MQTT broker implemented with Mosquito. This information are collected in a database, InfluxDB database, and can be visualized by means of dashboard with Grafana. Okay, so here we have the sensors by means of the Raspberry. We connect with the MQTT with OpenStack, and then it's possible to obtain information about the recharging values by means of user with a laptop and so on. Okay, this is the ICT infrastructure. In this, consider this infrastructure, communication infrastructure, we deploy the preventive security measures. In particular, we implemented TLS, both on publisher and broker communication, but also consider subscriber broker communications. So all this communication are wide area. So we use particular DSL communication technology, and we see how the inclusion of the TLS impact on the performance on the communication. So here we see on the handshake, so in the first phase of the communication establishment. And in these graphs, we see that in the red are plotted the plain MQTT measures. We have 1,000 runs. And in the blue, we have the values with the SEC MQTT implementations. As we see, the values are not so different. The peaks are due to the instability of the channel of the DSL communications, and are not related to the inclusion of the security. We see that are both in red and blue. So the most impact is related to the real network and not on the implementation of the security. Okay. Also here we see the frequency, and we see that is not so, the delay is not so impacting. Consider the topic message, so the measures messages. Also in this case, we see that is not so important the inclusion of the security on the performance values, but also in this case, we have some peaks related to the communications technologies. So we can see that the TLS could be implemented in MQTT communication in order to provide defensive preventive security. Moreover, in this implementation, this architecture, we have implemented also a monitoring platform. So we analyze some indicators related to, in particular, these are related to the broker. So the components on the cloud, the broker that collect the values coming from the sensors by means of the gateway. And from the monitoring platform, we can see some interesting information about, for example, of the possible attack vectors, considering the geography of the source of the attackers, but also the number of user authentication, quindi success or fail. The IP that will be used, we say that if in our architecture we have a specific IP, so the source and the destination are defined, are fixed. So if we have a lot of sources, this could be a sign of possible attacks. Another important information is about, for example, the frequency, the distribution over the time of the try of authentication. For example, if we image that in the night there is not information collected, the authentication try could be a sign of attacks. In particular, in order to test our anomaly detection platform, we have implemented some process of attacks to MQTT communication, in particular to MQTT broker. So this attack process is composed by different steps, and we see that using the monitoring platform and some techniques for correlation and analysis of evidence data, we have some alerts about the attacks, the attack steps that is that is active. Okay, so we have the alarm, and we have a dashboard where we see some information about the step of the attacks. This infrastructure is used not only for a specific electric vehicle charging collection of information, but also for other pilots. For example, we use for electric ship in Italian lake, for our RSC electric vehicle patrol, and also in a city for the bike for delivery of food. Okay. These are some examples of real implementation of these architectures. Okay, now move on the other example, other experimental setup that is related to distributed energy resources monitoring and control. So here move past 3. So we have the architecture is composed by different areas. So we have a control center, for example, a distribution control center. Here we have a part of a distribution operator area. So we have the distribution control center, the substation, and the generation, the distribution energy resources area. We have different control communication network, but also it's important to implement a specific network for the management, for the monitoring, and for the security aspects. So we have implemented the preventive measures related to, for example, TLS, from the communication control center substation and substation distributed energy resources. And we tested the performance of this communication considering mobile communication network. So we have tested the different types of technology of mobile communication for 2G, 3G, 4G, and the wired standard and the wired communication in order to compare the different performance. And we see that here we have 3 different distributed energy resources sites connected with mobile communication and 1 for wired. And we compare and they see that 3G, 4G are okay for the communication, also with the inclusion of security. both for handshake time, so for the first step for the establishment of the communication, but also for the round trip time related to report containing measures from the distributed energy resources to the substations. The next step is to analyze also 5G. This information could be collected also by a monitoring platform. So the implemented monitoring platform collect indicators related to classical IETF, so related to communication device or communication nodes, but also we have indicators related specific for the protocol for the context of the communications. So we see, for example, here the MMS, that is the specific protocol used for communications. So we collect information related to monitoring logs. All are collected in a platform that correlate this information coming from different sources and related to different types of informations. We used this monitoring platform in order to implement anomaly detection platform. So we implemented different emulation. We have emulated some different types of attacks, and we see that we have a detection, a recovery at the ICT level, and this information could be used in order to perform adaptive control in power site. Moreover, we use this use case also to test the use of emerging technology for the monitoring and control, in particular using single board computer, fog node, and cloud. So our test setup related to the communication ESC 618050 related from a single board computer to cloud, and we analyze this communication are performed in a real network using DSL connections. And here we see the impact of the performance of the communication. And we see that the most important is related to a handshake, where, for example, the security certificate are exchanged, and the delay is not so important, in particular considering the normal traffic, measured traffic. Okay, all this platform could be used for analyze the resilience of the power cyber systems, both using power simulator and ICT testbed, but also using field device, as for example our test facility where we have real devices. Okay, so in conclusion, we have that IoT fog cloud paradigms represent an important opportunity for the electro energy sectors. We need to guarantee secure and economic solution. We need to address the security by design principle, and we need to implement preventive but also defensive security measures. Okay, so as a future work, we move on with the different application communication technology, and we implement new preventive and defensive. The RSC labs that are involved in this analysis, so IoT and big data laboratory and the security laboratory. Here's some bibliography about our works. Okay, thank you. You have some questions? Any questions? Okay.
Some questions have been put in the chat box. Can you go through it, and any one of you can reply, please?
Allora, Here to the last. Allora, how much energy power is consumed at various layer stage? Yes, this is a very important aspect, in particular considering IoT devices, IoT sensors, because the inclusion of security could increase the consumption of energy. So sure, it's important to analyze also these aspects. Because obviously in higher level we have also different power supply, but in the field layers this could be a problem, sure. Okay. What is the present status of cybersecurity measure adopted by European power utilities? Are they up to date with the list regulation standard compliance? The European power utilities are ongoing to install, to follow the standard and the work in the working group related to the standardization. So it is important to not only provide the standard but also work with the utility in order to select the specific solution that could be implemented. And we have in Europe we have several pilots with test the solution with the security. Okay. Are IPU setting aside annual budget for? Okay. Giovanna, you.
Okay, yes, of course, the question of budget is one of the questions that also come up in the report I mentioned, that is the one on the network code on cybersecurity. And what is said there is that the cost of implementing an information security management system in a given utility depends on the dimension on the size of the organization, of course. So just to give you a flavor, they mentioned from approximately around 100 kilo euros and to 1 million euros. So covering from the smaller utilities towards biggest multi-energy organization, widespread geographically in different sites. So of course, I think that the values are not to be taken as absolute values, of course. They are just estimations to give a flavor, but they don't include, for instance, the full-time equivalent cost of persons and people, of course, that needs to be on the staff for managing cybersecurity infrastructures. So I think that a precise evaluation of the cost is not available. And of course, it's a matter also of discussion within the regulatory framework and also in Italy, for instance, with our national agency. So, of course, as soon as this regulation will come into place, these issues will be for sure addressed. And some remuneration schemes also in SIGRE, we have, I just anticipating what maybe I will say in my next and final speech, is that this is a topic, the topic of cost for implementing cybersecurity in power utilities, and the remuneration scheme from the let me say, for the government, from the public authorities, is a topic proposed for future working groups that will start maybe in late this year or beginning of next year, most probably. So I think that this is at the current stage a topic under discussion.
Hello, ma'am.
Okay.
There are
is
two more questions. I think you can reply. Any of you?
Okay. So can you please give your recommendation to keep the data in separate cloud for data analysis and recovery purpose, or local server database now to fulfill the purpose? No, another important aspect is related to the public cloud. If here we have a private cloud, so our data is in our systems, but in a public cloud, it is important where the data are stored. So this could be a different, and it depends also on the types of data, because data could be a different security assurance level related to the three different pillars: for confidentiality, for availability, for integrity. So depends on this, it is important to implement the correct solutions. Okay. Poi, this is economical to process data at edge or in cloud. Sure, could be important to process data. Depends on the data, depends on the process, because if we need, for example, very stringent latency, we need to process the data near the fields. So edge could be a valid solutions. For big data analysis, we need, for example, cloud solutions, because edge are not applicable for a big quantity of data. So depends of the use case, depends of the use. For control, for example, it's important to be very, for primary control or secondary control, it's important to be near the fields, the facilities. Okay. For a power utility, which is a certificate, okay, the flow, Giovanna.
Okay, I think that and it's also in the report on the recommendation for the network codes, is that for sure the 27019 complement the main part of the series with specific controls for energy system. And in particular, they said that there are at least 13 controls added. There are controls and also guidance for implementation that has to be taken into account. And this is specifically true for legacy systems, because one key issue for EPOs is to address legacy systems and, of course, the need to meet some specific security requirements, maybe through complementary solutions, because the standards let me say, are not possible in legacy systems. So there are a set of controls that need to be considered, and so yes, it's necessary to extend the analysis and the certification to controls that are specific also in part 19.
Is there any questions from participant side? Shall we can end the session, sir?
I think I'll just ask one question to Giovanna before we close.
Sure, sir.
Dr. Giovanna, my question is that your company RSE is a research organization on cyber field, and you are helping. Are you helping the European power utilities with implementation as well, or only the guidance? I think she is not understood, or maybe.
Yeah, she's mute. She's on mute.
Okay, okay.
Dondasola, please unmute yourself. Please unmute yourself.
Okay, so I just was saying that yes, of course, we as RSC are mainly carrying out research for, I mean, as funded by public funds from the government, and so our research is for the key and main utilities in Italy, and in particular we have of course collaboration with them, and also we act as consultant for the authority, and so we use to have this interlink. We are together in standard committees and in particular in the application of international standards into Italian norms. And so we are in the process, for instance, we are involved in this process of defining the Italian norms for the connection of distributed energy resources to the medium voltage grids. And in this case, we are in the process of including the application of the standard 62351 in this kind of communication between DERs and grid operators, distribution grid operators. So yes, in some way we are quite involved in the evolution of the power utility infrastructures.
Thank you, Dr. Giovanna and Dr. Roberta, as well as Dr. Mairo Todestini. I think you have covered the entire gamut of the cybersecurity. And within the short time, perhaps I think more than this was not possible. And your presentations are available to the participants. They will certainly benefit by this. Do you want to add something more, or we can close it now?
I think I have very short final slides for SIGRE activities on cybersecurity. I think they are quite relevant for the audience. Can you see the slide?
Yeah.
Okay. Okay. The structure of the study committee D2 is already known, I think, and so I would like just to show you which are the working groups that are currently active on cybersecurity, and you see they are marked with a specific icon for cybersecurity, and they are working in particular on issues on sensitivity of data and in EPU. And in particular, we have also one other working group, the 250, on contingency operations and the impact of cybersecurity measures during emergency. And then we have the working group 51 on security operation centers, so how they are implemented and the different architecture that are going to be in place. And then we have hot topics discussed and collected during the last regular meeting, and in particular from the different country reports 2020. And you see that the topics covers many issues from the certification schemes towards the implementation of 27,000 series, the issues of federated SOC and the shared SOC, the impact of COVID pandemic time on cybersecurity issues, and many, many others that you can find in the material you have. And also we have published along the years several technical brochures that addressed the evolution of the cybersecurity landscape also, and the evolution of standards also. And you see from the top to the down to the bottom that also very recently we had some publications that are for instance, the first one is also publicly available. And the Green Book that has been published in July 2020 includes specific sections for cybersecurity, and in particular in the state-of-the-art section, you have here the picture of the content that covers regulation, standards, risk assessment, best practices, and the link with resilience. And in the section on the evolutions, we have, in particular for cybersecurity, the issues related to intrusion detection, that is somehow, of course, related to defense side, but also towards what is anomaly detection that has been discussed and presented by my colleagues in the previous presentation, and in particular also the evolution on the sides of telecommunication systems and cybersecurity in new ICT platform and telecommunication technologies. Okay, that's I think all from my side. And thank you for your kind attention and also for the questions. I hope that everything has been, let me say, well received, and the material is in your hands. You can surely ask for additional clarifications on for more details by email. You have our contacts now, but we can keep in contact. Thank you.
Thank you so much, Dr. Giovanna and your team. I think it has been an excellent seminar, and we are really grateful to all three of you to have spared your time and also the extra time that you have given in answering questions as well as covering all the aspects. Of course, it is not possible to really cover, and explain everything in short time, but still I feel that to the extent possible, it has been, our audience have been benefited. I'm only requesting my Indian audience, that the membership on the, various working groups is not very encouraging from India. So I request them that there are so many working groups on SIGRE SCD2 committee and also on cybersecurity, as you have shown. They can, they can identify people from the organizations and write to the National SIGRE Committee for SCD2 participation in those working groups. So thank you all, and thank you, Dr. Giovanna and Dr. Roberta and Dr. Moiro, and thank you so much for giving your time and valuable comments and valuable presentations. Thank you so much.
Okay,
Ciao.
Okay, thank you. Bye.
And
Bye.
Bye. Thank you.
Bye. Bye.
Thanks.
thank you बोल के वापस आपको मिलता ये तो वही है सर जी खत्म
Oh. 30 इसको क्या करूं एंड कर दूं हैंग अप का है लीव कर दूं